Hi, this is an AP chemistry video. We're going to be covering 10.8 and 10.9 in our text. So, first thing we're going to talk about is vaporization, also known as evaporation. It's when molecules of a liquid escape from the surface of the liquid. So this is not boiling. All liquids do this below the boiling point. And it is an endothermic process. Energy is required to overcome the IMFs of the liquid for the liquid molecules to be able to escape. The enthalpy of vaporization, also known as the heat of vaporization, is the amount of energy that would be required in kilojoules for every 1 mole of liquid to turn into a gas. Condensation is just the reversal. Once you have enough, if you have a closed container, the molecules that vaporize, then eventually they'll start condensing and reach what we call an equilibrium. So an equilibrium is when overall there's no net change. It doesn't mean everything is stopped, but just the number of molecules that are going from the liquid into the gas equals the number that are going from the gas back to the liquid. When you have this gas above the liquid, it exerts pressure, and we call that vapor pressure. So this is representing that equilibrium point. In the beginning, its rate of condensation is lower because there aren't that many gas vapor particles. But then as time progresses, eventually you reach the point where the rate of the evaporation and the condensation are equal. Volatile liquids, some liquids like alcohols and nail polish remover, which is acetone, they have a high vapor pressure because they evaporate so easily. So there will be a lot of vapor above the liquid. And this is kind of showing you some more volatile liquids. This is the point, where you would have the equilibrium between the vapor and the liquid. And you can see that in these diagrams. I'll keep going. The vapor pressure of the vapor is in this part of the tube. You can see that it increases as we go from water, which is not very volatile because of the hydrogen bonds, to ethanol, and then to this is, I don't know what molecule that is, but that one's very volatile. So a lot of gas and a lot of vapor pressure. This is just showing you the vapor pressure as a function of temperature. So as temperature increases, more particles are going to have enough energy to become the vapor particles, and therefore the pressure would increase. This is trying to show you how the vapor pressure of 3 different liquids varies with temperature. And you can see that it's not a linear relationship, but if we do graph 1 over the Kelvin temperature versus the natural log of the vapor pressure, then we do get a linear negative sloped line. Which leads us to, and the book does a good job of deriving this formula using the equation of the line, y equals mx plus b. We aren't going to do that here, but this is an equation that we can use where we would take the natural log of the vapor pressure at the first temperature divided by the vapor pressure at a second temperature, and then multiply or equals the enthalpy of vaporization over R, which is the ideal gas law constant, which is 8.3145 joules per Kelvin mole. And then you would multiply by 1 over T2, 1 over T1. And these temperatures have to be in Kelvin. So the vapor pressures can be in any unit as long as they're both in the same unit. So here's an example of doing a calculation with that equation. So here we know that the vapor pressure of water at 25 degrees is 23.8 torr. And we know that the heat of vaporization of water at 25 is 43.9 kilojoules. So what we want is the vapor pressure of the water at 50 degrees. So what we have here are two temperatures, which we would need to convert to Kelvin to plug in to this part of the equation. We have the delta H, we know R, and we do know one of the two pressures here. So which pressure you set equal to pressure 1 doesn't matter as long as you then correspond that with temperature 1. So for this question, we're going to say that the pressure of 23.8, we're going to call that essentially P1, and the temperature that that water vapor has that pressure is 25 Celsius, which is 298 Kelvin. And then the second temperature is 50 Celsius, which is 323 Kelvin. So there is one conversion I do need to do in order for my units to cancel. I have to take my vapor pressure, which is given in kilojoules per mole, and convert that into joules per mole. So when I do that, I get 43,900 joules per mole. So now I'm ready to plug into the equation. So remember, the equation is the log of P1 over, let's say, P2 equals the delta H of vaporization over R, and then that's going to be 1 over T2 minus 1 over T1. Let me just double check I got that. And I did. So then they were plugging in. So we're going to plug in to that equation. And we can essentially take the natural log of 23.8 over the unknown pressure 2, and we know it's going to be equal to negative 1.37. So what we can do is do the inverse natural log and calculate that pressure. So if you have questions on that calculation, just keep watching. The next one, I'm going to show you how to do that. So the next question is a little different. So now we are going to be looking for one of the temperatures. So in Boulder, Colorado, we have a pressure of about 610 torr. And we want to know what would that boiling point be if the enthalpy of vaporization of water is 40.7. This enthalpy of vaporization is at 100 degrees Celsius and 1 atmosphere of pressure. So what we're going to do then is say P1, and it could be P1 or 2, it doesn't matter, is going to be equal to 1 atmosphere, which is 760 torr. And then the corresponding temperature is going to be 100 Celsius, because that would be the point where it boils. But we're going to convert that into Kelvin. And then we're going to set Boulder's pressure as P2. And we're looking for what would the boiling point be in Boulder. So we're still using the equation. So we're going to take the natural log of 760 over 610. And that's going to equal, we do need to convert that again. So it's going to be times 1,000, so 4.07 times 10 to the fourth joules per mole. So that's what I'm going to put in for my enthalpy of vaporization. And then my R value is on my formula sheet, joules per Kelvin mole. And then I'm going to multiply by 1 over T2 is my unknown, minus 1 over 373. So when I do the math here, I'll just show you my work. You can go directly to the answer if you want. The log of 760 divided by 610 natural log is 0.2198. This value here is 4,895. And I'm going to multiply by that 1 over T2 minus 1 over 373. So let me just add a page so I have more room. So essentially, and you don't need to show all this, but you do have to do the work. I'm distributing this through. And then what I will get is, if I combine these terms, I'll get 13.3398 equals 4,895 over T2. So if I multiply both sides by T2, and then I will have this divided by this. And I didn't keep track of my units there, but you definitely can. So when I do this, I end up getting 367 Kelvin. And that, if I were to convert back to Celsius, is 94. Normal boiling point is 100. It's going to be lower in Boulder because of the elevation, and not that much lower because Boulder is not that high in elevation. It's around 5,000 feet.